So the next reaction we're going to cover is the acid-catalyzed hydration. Now the great news about all of this type of chemistry is you're going to start to notice a lot of reactions that look borderline identical. The hydrohalogenation that I just covered and this reaction are one of those sets of reactions that have a ton of similarities that I will draw your attention to. Now, acid-catalyzed reactions occur in multiple steps and are classified as ionic reactions, as you just saw. These proceed via a carbocation intermediate and also have Markovnikov addition for a regiochemical outcome, where Markovnikov addition means the higher priority group is added to the more substituted carbon atom. Here we'll have addition at the carbocation intermediate, remembering that a carbocation is sp2 hybridized. And since it's sp2 hybridized, it's flat. It means we can have attack from top and bottom face with equal preference. This means that I should get a 50-50 distribution to give a mixed stereochemical outcome, if that matters. This is called a racemic mixture if there's only one stereocenter. Now keep in mind that hydration reaction means the addition of water. So we're going to be adding a net of H2O across the alkene. The reaction is shown here, where again, you're going to note that the higher priority group, in this case the OH, is added to the more substituted carbon. The hydrogen here, which is lower priority, is added to the less. And the alkene is transformed to an alkane. You'll notice that we have added H2O across this bond in the form of H and OH, and we'll see why that is when we cover the mechanism. Now, the last thing I'll draw your attention to is the fact that this reaction is acid-catalyzed, which means that we need to add a proton source in order for this reaction to proceed. This uses typical strong acids like sulfuric acid and hydrochloric acid. Anytime you see H2SO4, this will be a catalytic acid, a source of the proton, or H+. Keep in mind that there's a lot of equivalencies in organic chemistry. So if you see H2SO4, this means that you have a proton source, which can commonly be written as a hydronium. All of these are synonymous with each other, so keep that in mind as you're working through organic chemistry problems. As we did before, now let's work through the mechanism. So the steps of the hydrohalogenation are also going to look really similar. First, we're going to have addition of the hydrogen atom from the acid to the alkene to generate a carbocation. There may be carbocation rearrangement, again covered later in this chapter. We then have nucleophilic attack of the water nucleophile onto that carbocation. This is all in line with what we saw with hydrohalogenation. There is a last final step here, and that's deprotonation of the nucleophile to give the final product. Let's take a look at how all of this works. Again, we want to identify the nucleophile and the electrophile. The nucleophile will be here. That will be the alkene acting as the nucleophile here. And again, we're going to have an electrophilic hydrogen atom because of the bond dipole. What we will get when we do this reaction, and I'll show the HCl drawn out with a bond, is attack of the nucleophile onto the electrophile with departure of the chloride anion. At this point, we will generate our carbocation intermediate. What you'll remember from our last section is that we ask ourselves the question, what is the best carbocation here? So is there a way to have a more substituted carbocation? In this particular example, there isn't, because both of these carbocations would be created equal. Here, I'll show the hydrogen atom being added to the bottom carbon, but I could have added it to the top. I now want to bring in water as the new nucleophile. Now this is nucleophilic because of this lone pair. Now we saw the halide being the nucleophile in the previous example. The reason why it is not here is because water is a better nucleophile and it's present, which means it will do chemistry. In order to do the hydrohalogenation reaction, we work in non-nucleophilic solvents. Here, we have a nucleophilic solvent, so it's going to do chemistry. This lone pair will attack the electrophile like so. From the top and the bottom face, I'm going to draw the top face attack, and I'm going to label that for whoever's reading my answer. In this case, it's all of you. But if I was doing this in a testing type scenario, I always like to indicate to whoever's about to read my work what I'm actually drawing. Here, I say top face attack. I will draw the product of this reaction at that point. Here's that methyl group from earlier and the hydrogen atom, and I will show top face attack of water, which means I need to show bottom face with the methyl. Now you remember that an oxygen with 3 bonds always carries a positive charge. At this point, I now need to bring in water to do one last step, and that's to abstract this hydrogen atom, to regenerate the catalyst. That's what a catalyst means. It's present at the start and is regenerated at the end. So I need to regenerate that catalyst, and I need to give a neutral product. Hydrogen is abstracted. 2 electrons in the hydrogen-oxygen bond go to the oxygen, and I am left with my final product here. OH group up, methyl group down, and the methyl and the hydrogen here. I have to ask myself the question, is this a chiral product? The answer is yes, which means that I should draw the other one as well, like so, where I'm going to have the methyl group up, the OH group down, like so, a methyl and a hydrogen, and again, I will get 50-50 distribution because attack of a carbocation does not have preference for top and bottom face. So to recap, we have the nucleophilic alkene abstracting the hydrogen from the acid catalyst. We form a carbocation intermediate, and we have to ask ourselves the question, are we making the best carbocation? Once we've generated that intermediate, we then attack it with our nucleophilic solvent, water. And then the last thing we do is we regenerate our acid catalyst, and we give ourselves a final neutral product where we double check if stereochemistry matters. It does here, and so we indicate both products and their distribution. Now there's a chance for you to practice on the next slide. So as with before, you're being asked to predict the product of this acid-catalyzed reaction. We know we should get Markovnikov addition. We know that we need to watch for top and bottom face attack should we make something chiral. I will draw the product here. There's only one alkene to do chemistry. I'll show the hydrogen being added here. You'll notice that I can maintain the stereochemistry at the non-reactive site. If there's stereochemistry indicated, make sure you carry it through, especially when it's not doing chemistry. It means that it's unaffected. I then am going to indicate that I have a methyl group here and an OH group here. And I ask myself the question, is this product chiral? The answer is no. And so I don't need to draw another product because there's no important chirality here. And that's it. That's the product of this reaction. So hydrohalogenation and hydration of an alkene, very similar, where we get Markovnikov addition, we have a carbocation intermediate, and we check for chirality because of attack of this sp2 hybridized carbocation.